One. All right, so we're picking up with example 3 in the newly revamped, edited 3.5 notes, which you can only find in Canvas. I haven't put them on the World Wide Web yet, but they will be there eventually. I'm going to try and pace it so that from now on we spend 2-3 days max on one particular subject. The next 2 subjects after this might be those exceptions to the 2-day rule. Okay, we'll move swiftly and quickly, and of course then we're going to rely on you to get in the reps outside of class so that you master the skills. Now, again, I'm on a lot of like forums with AP Calculus students and teachers, and it's becoming more of a problem every year for me to keep up with the others, you know, and it's okay. I don't need like Noom to tell me, you know, how I was raised and why that is. They kind of tap into your psychological reasons, like, oh, I was raised to clean my plate. That's why, well, you know, that kind of thing. I know why. It's quality over quantity. It's the reason I actually got out of the home building business, because when I first got in, I worked for a company that we called them track homes, right? There were like 5 or 6 homes, and I was in charge of getting them built in 77 days. And there were some modifications that the homeowners could make. Pretty much, it was one of those floor plans. It was on this lot, and 77 days is not a lot of time. And I had like 13, 14 houses at one time that I was keeping track of. The first one that I did, when they gave it to me to start me out, I babied that house, you know, because I have a woodworking background. I was a cabinets apprentice for many summers, and I built things, so I know about construction. And man, I nitpicked that house, and every inspection would pass with flying colors, and I was really, really proud of it. But when you got 13, 14 going on, it's really, really hard to make sure that they're all up to your standard. And so when the flood hit, that's when I got out and tried it on my own. But I'm too nice of a guy. I don't have a lot of business acumen. So even though when I built them on my own, I built them how I wanted, slowly, it just wasn't profitable. So anyway, here I am. But I am a quality over a quantity kind of guy. And I think of like most AP Calculus classes that are beyond where we are, they're doing that plantation home stuff. It's all stick framed, we call it, right? You just got lumbers, you throw it up, it's going to hold, it's going to last. But underneath there, it's not going to be like an architectural structural masterpiece, you know. I'm going more slowly. So we talked about the limit being the foundation, but at every step, we're kind of building foundations for higher level stuff, whether it's calculations or more theorems to come. We're getting into the math. We're not just answering the questions how as we go from one subject to the next. I'm hoping that we're addressing the why as well, you know. And so that's it. So, you know, I hear this often, that students go off to college from here, and whatever you made on the AP exam, some students didn't even take the AP exam. They end up being like the stars. If they end up retaking calculus, they end up being the stars in their class. Everyone finds out that they're the ones who actually know how to do stuff. You know, they may not have gotten as far, you know, but they understand what they did. So that's kind of what I'm hoping for. So it's always been this tug of war between quality and quantity. Pace, I got to get through it. Pace, but really going in and looking at the corners a little bit and making sure that everything fits, you know, not just a sloppy joint and a rafter where it meets the ridge and there's a gap there, and so you put 15 nails into it, right? 15 nails into a 2x8 will hold it, but at a certain point it kind of defeats the purpose. It weakens the board actually instead of strengthening it. So that would be me going too fast and y'all not understanding what we're doing. There's no way to build upon that. So just kind of keep that in mind. But the pace, you know, the pace is kind of one of those things. If I don't get you the reps in, you know, and get you to the AP exam, I feel like I'm failing you as a teacher. But on the other hand, I feel like if you understand it, you know, you can be like Nelson Mandela. You can be in prison for years and years and years, and they're not going to be able to ever take your calculus away or your hope and faith in humanity, right? You're not going to be able to take it because you got CSU, baby, and you got math in you too. It becomes part of you, right? So anyway, I just want to throw that out there for my own benefit, if not y'all's, right? It makes me feel better. I'll sleep good tonight. All right. You know who's not sleeping good tonight? The Dallas Cowboys. Oh my gosh, they didn't sleep good last night. Too soon, right? Too soon. Okay. So if you're ever out, I do record during class. And so like Juliana's over there on Zoom, you can log in live, but remember, I'll always throw the video into the shared folder. Okay. So happy National Gourmet Coffee Day. Happy birthday, Jonathan Davis, the lead singer of Korn, 51. And A.A. Milne, the guy who wrote Winnie the Pooh. You need to know that to be culturally literate in America. Who wrote Winnie the Pooh? A.A. Milne. Okay. A.A. Milne. Now I say what? Is it? Yeah, that's cool. So I collect quotes like some people collect parking tickets. You know, I get a lot of them. I have books that I just read. You know, quotations that I read them from start to finish. You know, but this quote that's a quote of the day I hadn't come across before. I know the sentiment. The sentiment's been around a while, but this says that the nice thing about quotes is they're just little kernels of wisdom, right? The ones that last and endure are all these like big ideas that are condensed down into these little nuggets of wisdom, like sunbeams, right? Words are like sunbeams. The more condensed, the more they burn. That's another quote. But the flower in the vase smiles, but no longer laughs. I like that quote, right? The flower in the vase smiles, but it no longer laughs. So way to go, Malcolm. If you really reflect on that, that might change your whole philosophy moving forward. I don't know. Yeah, it moved me a little bit. It moved me a little bit. Yeah, it moved my mental cheese, if you will, my schema. From you? Oh, I bet they're good. Maybe after the AP exam, we could do like slam poetry and you can get them and read some of it. Okay. All right. So let's go ahead and jump into example 3. All right. VIP, very important person, a very important problem. That's what this stands for. Okay. These are typically free response questions. And any one of these questions can show up, of course, as a multiple choice. But as a standalone free response, they're really nice. Okay. So whenever you're given a graph, whenever you're given an equation, whenever you're getting given a set of data that describes a function, you really need to take stock and inventory. What is that the graph of? And how am I going to use it, right? The graph of the derivative f prime of a continuous function f from 0 to 9 is shown below. Answer the following questions. So it tells you that that's the graph of f prime. It even will have it labeled. That's the graph of f prime. So whether you write it out or you say it to yourself mentally, okay, the y values of f prime are the slopes of f, right? You're just processing that. So when you look at the y values on the graph, wherever the y values on the graph are positive, the slope of f is positive and f is increasing, right? And wherever the graph of f prime is below the x-axis, negative, the slopes of f are negative and f is decreasing, right? So that's how we process it. What are the y values telling us? And then, again, you want to at least think to yourself, what do the slopes of the graph give us, right? So now the slopes of the graph of f prime, they are the concavity values of f. Okay, so you always want to think of that second derivative kind of in 2 ways. First of all, what does it tell you about the original function 2 derivatives ago? It gives you the curvature, right? So again, you look at the graph, wherever f prime is increasing, f is concave up, right? And wherever this graph of f prime is decreasing, f is concave down. Now, we don't ever justify by saying increasing and decreasing. We would say the slopes of f prime are positive. The slopes of f prime are negative. But that helps us with that. And then you also want to think of the second derivative as being, what does it tell you about the first derivative? It tells you about the rates of change, right? So again, where the slopes of this graph f prime are positive, we know f prime is increasing. The slopes of f are increasing, right? Second derivative gives you 2 things. It's like saying it gives us the acceleration, but it also tells us how the velocity is changing. Okay, so just those 2 little things before you jump in can really expedite how you answer any one of these or all of these questions. Okay, this is the graph of f prime. Ready? Let's answer the questions. Letter A. On what open intervals? Now that implies what intervals? X or Y intervals? It implies X intervals. So for what values of X, open interval, is f decreasing? It's going to ask you to justify. Well, we've already thought about that. F is decreasing when f prime is negative. So all you got to do is come over here and find where the graph is below the x-axis. I'll even highlight it. Okay, so now in a complete sentence, f is decreasing, which I'll just put DEC on. Now, if you want, you could put x epsilon. This is optional. They didn't do it in their question, but hey, if you want to have it, you can. F is increasing on the intervals, and it says open intervals, right? So that's going to be from 0 to 1, union 6 to 8. Now, at this point, if there were any units, we would list units like seconds, right? But there are none, okay? Now it said to justify, so we'll just put a comma, because what's the reason? We always talk about a sign or a sign change. What is it, Mason? Yes, good, good. The y values of f prime. You could say that. That's absolutely true. But I'm just going to say because f prime is less than 0, and that's just a quicker way to say it, right? On these, judicious use of a pronoun, intervals. So you always have to say the x value or the x values interval twice. Here's where this behavior is exhibited at that point, or the intervals, because that also happens to be the place, the location where this happens in this manner, right? Okay. Now, how could you lose points for that? If you just said because the y values are negative on this interval, would that get it? The y values of what? There you go. Okay, so you're kind of getting in that little snarky mood too. You know how to like, yeah, right? The y values of what? The Lusitania? Make up something stupid. Yeah, definitely. Right, definitely decreasing. Okay, and that's it. So again, it's not going to ask you to like be totally thorough. If this were an actual pre-response question, it knows that if you can answer where the function is decreasing, you know that you can answer where it's increasing, right? Now notice that this is a slightly different question than if it asked on what intervals. If it didn't say on what open intervals, but on what intervals is f prime negative from 0 to 9. Now you would have to include 0, right? F prime is actually less than 0 on the half open interval from 0 to 1, union 6 to 8. Okay, so notice it's a slightly different question. Why would we have to include 0 if it asked just where the derivative was negative? Well, because it is a negative value there, right? But at the others, it's the x-intercept. Okay, so slightly different question. Okay, part B, at what values of x does this have a local max or min? Justify. Well, local max or mins can only occur at critical values. So real quickly, let's identify our critical values of f. We're not going to write it down, but critical values of f are where f prime is 0 or undefined. This is the graph of f prime. Is it ever undefined? From 0 to 9, is this graph ever undefined? No, it exists everywhere from 0. So there are none of those. But is this graph ever 0? Yes, at 1, 6, and 8. So those are your critical values. If it asks you what are the critical values, those would be the critical values. Now, once we ascertain that it's a critical value, we can do the first derivative test here because we have first derivative information, okay? And we don't even need to make a number line chart. Why? Because a graph is better than a number line chart. The graph gives us not only the signage, it gives us the relative values. So let's look at 1. Immediately to the left of 1, f prime is negative, and immediately to the right of 1, f prime is positive. So when f prime changes from negative to positive at a critical value, f has a what there? Negative derivative means decreasing, positive derivative means increasing. So that would be a local min. Is that what it asked us? Well, yeah. This one asks us for both, okay? Sometimes it might only ask you for just the one. What about 6? Positive to negative, that's a local max. And at 8, negative to positive, that's another local min, right? So when would it not be a local max or min? If the graph did what at one of those? Instead of crossing, it would have to, what's the word? Yeah, boing, right? Bing, bong, boing, boing. It would have to bounce. It would have to bounce. All right, so we need to list the critical values first, okay? That's the part that a lot of people will skip. We haven't like had an equation. We didn't set it equal to 0. We didn't name the critical values yet. So we have to do that first, okay? F has critical values. I'm going to abbreviate. You can abbreviate CVs and PVs every day except the AP exam, which is always falls incidentally on National Non-Abbreviation Day. So we celebrate it. F has CVs at X equals 1, 6, and 8, 1, 6, 8, because I'll just keep it over here on the left, because F prime equals 0 at these, there it is again, points or locations or X values. So I've stated it and I've stated why. All right. Now, if one of those was a bounce, since it didn't specifically ask for all the critical values, I wouldn't even have to mention that that one's a critical value. But because they all cross, I do have to mention all of them. So now we can answer the question. F has local mins. Now here's the question. Do we put of y equals at X or just at X? What did it ask for? Did it ask for the minimum value itself or the X value? Yes, okay. And that's a typical thing because it's a time saver. We really don't even know what the y values are, right? Thank goodness, because we just have the derivative. F has local mins at X equals, now we can group them together. 1 and X equals 8, comma. And the reason would be because, do we say because F changes from decreasing to increasing there? No. I mean, that's true. That's not a justification that we want, because F prime, and again, don't say because the graph, don't say because the y values, just call it F prime. Now, if you want to say the y values of the graph of F prime, whew, that's a lot more writing, right? The y values of the graph that's given above of F prime, that's a lot of writing. Just say because F prime, which is given, changes from negative to positive at these points, and again, there's referring back to them, comma, and now we can go to the other one, and a local max at X equals 6, comma, again, because F prime changes from positive to negative, and don't stop there, at, now I can either say this point, because it's a singular one, this point, or I can say X equals 6, which I'm going to do that. You know why? Fewer keystrokes, right? Now there is some valid trying to keep the pronouns the same, right? This and these. Yeah. Yeah, that's okay. Yeah, you can use the at symbol. That's common. Yeah. Mm-hmm.
Do you have to include that left side, or is that right for justification enough?
No, you have to include this. Yeah, that's what I was saying, that some people that jump straight to here will not get full credit. Okay. I have to declare them as candidates first. And because usually up to this point, we've had an equation, we've taken the derivative, we've seen where it was equal to 0, and we manufactured the X values on our own. So that lists them as candidate. Here, we're just pulling random values off the graph, and we need to know why those are the candidates. Okay.
Because changing from positive to negative is not only, like,
yeah.
Changing from positive to negative, it's still not be a local max.
Right. I mean, you could have a graph like here's F prime, and you can have a positive there and a negative here. And here's F prime, and here's X equals C. Now, X equals C could still be a critical value, right? Even though F prime is undefined there, it could be a critical value if F had a discontinuity or didn't exist there, right? That's why it's important. Okay. Now, this one did tell us, and this is why it says F prime is continuous. That's good. But we really don't know about F. So if it were this, unless it said F is defined at all values, we wouldn't know if this is a critical value or not. This could be a vertical asymptote, right? And we're not going to call a vertical asymptote a local max or min. So yes, it is important to always get your candidates first. And if it's from a chart or if it's from a graph, we have to declare them as such. If it's an equation, us finding them is good enough. Great question. I'm glad you asked that again on the back end because that reiterates it. Okay. Can't have one without the other. Just like pivotal values. You have to declare pivotal values first before you declare inflection values. CVs are to local max mins, as PVs are to inflection points. Okay. All right. On what intervals now is F concave up? We're asking about F. F is concave up, not when this graph is concave up, right? So again, we're mentally thinking, if I want to talk about concavities of F, that's second derivative information. So if I have the first derivative there, the second derivative of F would be the derivative of F prime, which if I don't have the equation and it's not the actual derivative, it's the slopes, right? So if we hadn't thought about it yet, now's where we think about it. So now I want to know where F is concave up. Now notice it says to justify. You can actually justify on the front end of answering it. Did you know that? And if you do that, it actually speaks to yourself. You're speaking to yourself. You're giving yourself something to find. So here's your thought process. Let's see. F is concave up. Now, here you can't just say when the second derivative is positive. That's not a good justification because you're not telling me what it is about the graph of F prime that you're looking at, right? Unless you come up here and you make this blanket statement, the slopes of F prime are the concavity values of F, which are F double prime values. If you make that blanket statement up at the top, then you can start talking about F double prime because now it's like a key, it's a legend. F double prime, oh, you're looking at the slopes of this given graph of F prime. So don't just be throwing it out there. But again, if we have the equation and we're finding F double prime, it's all good, okay? So let's go ahead and justify on the front end. I want the second derivative to be concave up. Well, that's the slopes of F prime. So I could say the slopes, I don't even have to write a complete sentence. Slopes of F prime are greater than 0 on, and now I'll give myself something to look for, right? The slopes of F prime are not only F double prime values, right? When you talk about slopes of a function, that's its derivative, you're giving yourself something to look for now. Where are the slopes of this graph positive? Well, it's where this graph is increasing from there to there, there to there, and there to there, okay? Now, again, you don't want to just say, since the graph of F prime is increasing on these intervals. That's technically not incorrect, but it's not a linchpin argument, okay? You also want to talk about a sign or a sign change, and you have to relate it to what it is you're looking at, okay? So slopes of F prime are greater than 0 on, and it did say intervals, so we'll list the open intervals, you should be fine. 0 to 2, 3 to 5, right? On X interval, this is again optional. 0 to 2, union, 3 to 5, union. I think there was one more at the end, right? 7 to 8. Yeah, union 7 to 8. It's understood that those are X intervals. So if you don't want to put the X in, that's okay. There's no units. Yeah, 7 to 8. And then it said to justify. So we would be then comma. We don't need to write anything else, right? Why wouldn't I need to say because after that? Put it in the front. The slopes, oops, that's where that went. I moved it and I lost the prime. The slopes of F prime are greater than 0 on these intervals. That's like a 2-for-1 sentence, okay? You're justifying on the front end. The person looking at your paper knows exactly what you're looking at. Exactly, okay? And now you're answering the question. And if there were any units on the x-axis, like, you know, time, you would put units at the end, seconds, whatever, okay? So you have that option. Otherwise, you would say F is concave up on these intervals because the slopes of F prime are greater than 0 on these intervals, okay? Now notice I didn't put F is concave up when the slopes of F prime are greater than 0, like I did up above, and that's okay because this is the only question that's being asked in this section. So I can go straight to this answer right here, okay? All right, state the inflection values of F. Justify inflection values, okay? So that implies X values, not Y values. So let's look at our PIVs. Your possible inflection values are where the second derivative is 0 or undefined. Again, what are we looking at? We're looking at the slopes. Are the slopes of this graph ever undefined? That would be looking for cusps or vertical tangents or discontinuities. No, okay. Then we look to see where, if ever, the slopes are 0. Are they? Yes, horizontal tangents at 2, 3, 5, and 7. 2, 3, 5, and 7 then are your pivotal values. If you want to state all of them, that's fine. But to be true inflection values, to be elevated from pivotal to inflection, from possible IV to full-fledged IV, we need a sign change in the second derivative, which means we need a sign change in the slope of f prime. Let's look at 2. The slope of this graph goes from positive to negative at 2. Is that an inflection value? Yes. At 3, the slope changes from negative to positive. You're in. Very good. At 5, positive to negative. Yep. And at 7, negative to positive. Are they all inflection values? Yes. All the PVs, possible inflection values, are full-fledged inflection values. Okay. When would it not look like 1? If it went like this and went to 0, and then it went up like that. Okay. Now, if it did that, it would be a positive derivative on both sides. How would you know that that's actually a PIV? It would tell you in the description. It would actually say the graph of f prime has a horizontal tangent at x equals whatever. You would be given that because it's hard to tell, right? But for a local max or min, it's not. So here's something else you can add to your little mental chart. Let's use a different flavor, beefy brown. Okay. The local extrema of f prime are the whats of f. The local max or mins. We have 2 local maxes and 2 local minses. Not just the pivotal values. They're the full-fledged inflection values, right? Yeah. You could say the critical values of f prime or the pivotal values of f, but when we actually see a peak or a valley, that's going to be an actual sign change. So the local extrema of f prime are the inflection values. Okay, not the possible, the full-fledged welcome to the club, card-carrying members. Okay, sweet. Now, it does say to justify. That's going to be a whole heap of writing. Okay, so again, you're not going to be asked necessarily to do all of them. You might just be asked to say, at x equals 2, does f have an inflection value or not? Okay, so let's go ahead and kind of frame the argument here. We would say the slopes, or f, here, do this, f double prime equals the slopes of f prime. Now you've stated that. So now if you want to start throwing f double prime around, you can. Those are going to equal 0 at x equals, and then we throw them out there, 2, 3, 5, and 7. Now, if you want underneath here, you could label those as pivotal values. Okay, if you want, you're not going to get credit for that. But now we've identified the candidate list. So do we need to do that first, Hank? Before we talk about a sign change there? We do. Okay, so it's just like saying that the local extrema can only occur at critical values. Now that we've got them in the pivotal value club, let's just do the let's do this. You can group them all together because we don't make a distinction between local max and min ones. So f has inflection values at, and we can list them all, x equals 2, 3, 5, 7, comma, because, and now we can have to justify them separately. That's crappy. So let's look at the 2 local maximums. That's going to be at 2 and 5. Okay, so we would say because the slopes of f prime, the slopes of f prime change from positive to negative at, now we can't say these points, right? At x equals 2, 5, and then we have to do it the other way, right? They always want to know how it changes. And from negative to positive at x equals 3 and 7. All right. So you see the subtle difference there? We can group them all as inflection values, but we justify them separately. And you can do it in the same sentence. So if you had to just do one of them, like if it said determine if f has an inflection value at 2, you would say, first of all, f double prime of 2 equals 0. And the slopes of f prime change from positive to negative at x equals 2. Therefore, f has an inflection value at x equals 2. Okay. Let's do that down here. I think I might want to kind of just add that. Let's just say, if it asked you at x equals 2, how would you justify it altogether? Well, you would come up here certainly and look. At x equals 2, f prime has a horizontal tangent, and the slopes change from positive to negative. So here you would say, this: slopes of f prime equals 0 at x equals 2. If you hadn't already said that the slopes of f prime are f double prime, and change from positive to negative there, or at x equals 2, comma, so f has an inflection value, not in France, but at x equals 2. So that's how you would do them one at a time. And again, Hank, is this first part important, saying that the slopes of f prime are 0 there? Yeah, you don't have to say the word pivotal value. You don't have to say the word critical value. But if you haven't already found them yourself, they haven't been distilled from the derivative process from an equation, you have to grab them and state them from a table or a graph. Okay. So really, when you're doing inflection value justification, it's really the same framing as we do for local max and mins with the first derivative information, right? Just always relate it to what it is you're given. So be careful just throwing around f double prime equals 0 at x equals 2. Okay. All right. And then finally, the last two. And this is where kind of I combine some of the lessons. You should be able to, from a given graph, you should be able to sketch both the derivative of it and higher order derivatives from it. And you should be able to sketch the antiderivative. What is the antiderivative? That means going backwards. So if I have f prime, I should be able to sketch f. Now this one's asking us to sketch f double prime first. So to make this pretty, here's what I would recommend. And you can do this with Notability. Let's add a page. On the AP exam, you might have to sketch it. They might give you a new graph. I'm just going to temporarily delete that. You might want that still there. So now that it's gone, because you can copy an image, right? As long as there's no handwriting on it, you can copy the image. So let's copy the image. And then on a new page, let's put that. And we'll do it twice. Okay. We'll do it twice. Boom. And I'll get rid of the whatever. Oh, I grabbed the 10 along with it as well. Okay. And now I guess, can we undo? I guess we can undo. If you undid before I pasted, will it keep it in the clipboard? I could, sure.
When I did it, I cut my drawing.
Oh, and you moved it down? Oh, okay, that's good. Yeah. So the point I'm trying to make is if they had you sketch something on the AP exam, it would be either one graph on top of one they gave you, or they would give you like a new set of axes to do it. So you could start fresh, right? All right. So let's go ahead and do on this one here. We'll do this one as part E. Part E, right? Oh yeah, it's a part E indeed, isn't it? Yeah. You know who's partying today? Jonathan Davis. Right, it's his birthday today, lead singer of Korn. There's a party hat. And so is A.A. Milne. He's partying right there. Yeah, with Pooh and the gang. We don't need a starting point to sketch the derivative. So here's what the thought process goes. When you're given the graph of f or f prime, doesn't matter. You're trying to sketch a derivative. Okay, here's what you need to calibrate yourself for. I must graph the slopes of, in this case, f prime at the same x values. Okay, so whether they give you the graph of f and they say sketch f prime, or you're given the graph of f prime and they're asking you to do f double prime, or hypothetically, you're given the graph of f, the 52nd derivative, and you're asked to graph the 53rd derivative, right? Whatever it is, you're taking the derivative of some function and you want to sketch its graph. Okay, if I need to plot the slope values of f prime, I need to first go to the graph of f prime and look to see where the slopes are an actual number. Okay, because other than that, it's more of a qualitative analysis. I don't know if the slope is +1 or +1.5, but I do know that there's one place where the slopes are definitively a number. And where is that? 2, 3, 5, and 7. I know the derivative there is what, Hank? 0. Those are your horizontal tangents. So that's what you're going to do first. Go to any horizontal tangent. You may not have some. And in the case that you don't have some, you're going to have to do the qualitative stuff that we're going to do now. But I have 1, 2, 3, 4. I have 5 pivotal values. Okay, those are going to end up being the zeros. Now, because this looks polynomial-esque, right? It looks kind of like a polynomial. Remember, when you take the derivative of a polynomial, you lose a degree, right? X cubed becomes x squared. So what that means is you lose a hump, right? You lose a local max or min. So this one has 1, 2, 3, 4. It has 4 humps. Our graph should have 3 humps. Okay. Now here's what you do. In between the zeros, and we've done this once before. In between the zeros, you look to see, first of all, is the graph increasing or decreasing? This graph, whatever you're calling it, is increasing, 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 right? So on those intervals, I need to have my y values of the graph be positive. Yes, I need to have positive values here. I need to have positive values here, and I need to have positive values here. So we're looking between the x-intercepts, yeah? Okay. Now, if you look where the graph is decreasing, the graph is decreasing here in green and decreasing here. That's when my graph needs to have negative y values here and here. Okay. That makes sense. We've already kind of used that aspect of the graph, right? When we're talking about inflection values. So now how do we draw it? Well, because it's kind of a polynomial, let's look to see how now. So let's go from left to right. I'm going to use red. If you think about a tangent line right here, here's a tangent line, and then here's another tangent line right here. Okay. All we can do is compare from left to right. They're both positive tangent lines, right? But notice the tangent line I drew on the left is much steeper than the one I drew on the right. Yes? So this is where your qualitative analysis comes in. Your slopes then are doing what as we approach 2? The slopes of f prime are decreasing, approaching 0. The slopes are getting flatter. So now I'm just going to draw it coming down. I don't know where, but I'm just going to have it come down like this. Now, really, we should put an open circle at the end, because remember, does a derivative exist at an endpoint? No. So it's going to look more like a polynomial. It's going to be kind of curved upwards. It's not going to come in like this necessarily. Polynomials keep that kind of open curvature. Now, watch this. As I go from a slope of 0, right about here at the inflection value, that's where the slope is the most negative, right? And then after that, it starts to increase its value back towards 0, right? So I don't know how low it goes, but right there at the inflection point, where it was the most negative, that needs to coincide with my lowest point. Okay. In other words, the inflection values of this graph should be the local extremas of the derivative, right? We've already looked at it the other way around. All right. And then after that, the slopes are positive, but right around here, and again, you're eyeballing it. You can't pinpoint inflection values. Right around there, that's where the slope is the most positive. It's the steepest in the positive direction. So again, I don't know if that happens at 4 or let's say just to the right of 4, but it hits the high point. So it's going to come up like that, and then it's going to start getting shallower and coming back down, approaching 0. And then we just kind of keep that process going. On the next interval, the function is decreasing, but maybe somewhere in here at the inflection point, that's where it's the steepest in the negative direction. So that's where it's the lowest. And again, I don't know if it's at 6 or 5 point whatever. And then I'd come back up. And then finally to the right, the slopes just keep getting steeper and steeper, don't they? So I'll just kind of finish with my graph until I get to the endpoint at 9, and I'll put another open circle. Okay. So that's a possible graph of the derivative. Now I'll label it as the derivative of my graph. Well, if my graph was called f prime, this is going to be f double prime. Let's count the humps. The blue graph has 1, 2, 3, 4 humps, or 4 local extrema. How many humps or local extrema does mine have? 1, 2, 3. Okay, so that's another way to check. Now it's going to look kind of like this open W. What we don't know though is the Y values of our local max or mins. I don't know really how low it goes. I don't really know how high it goes and how low it goes. And I don't know the X values where they occur. You're just kind of eyeballing it. Okay, if you're graded on this kind of work, it's a very subjective thing. But open circles at the endpoints, yes. A derivative does not exist at the endpoint. So as long as yours look W-ish, they're going to look to see if it looks like a W. And here's the other criteria they're looking at, as you can imagine. They're looking to see if these inflection values, which again, we're kind of eyeballing them. They're looking to see if those inflection values line up, you know, in the X coordinates as your local max or mins, right? Now, if you want extra practice, you could sketch the graph of f double prime, right? You could take the graph of your red one or my red one and sketch its derivative. Your first start would be to go to the 3 local extrema and put yourself some x-intercepts down, right? And do the analysis all over again, okay? All right, how does that sound? All right, now there is an example further down here. Well, there's not, I got rid of it. Before we go on, let's look at this. What if I have, let's try this. What if I gave you, ooh, that's not a horizontal line. Bad. Okay. What if I gave you just this graph right here? It looks like this, and it looks like that. And let's call this f triple prime. And I want you to sketch the 4th derivative. Okay. Well, you might recognize the equation of this guy, right? Or what family he belongs to. What is it?
Oh, it's
The 1 over x. So again, if you can identify what it kind of looks like, or at least the family, you could say, oh, well, I'm going to take the derivative of that in my head. That's x to the negative first. So it's going to be a negative 1 over x squared. Got it. And then you just graph negative 1 over x squared. Okay. But it doesn't necessarily even have to be that equation. Let's see if we can sketch the derivative. First things first, we look for any local extrema. Does this graph have any local extrema? No, crappity crap doo-doo. Okay, not a problem. So I can't put any x-intercepts down. So now I'm just looking at the next thing. Are the slopes positive or negative? And if so, are they becoming more positive or more negative in relation to the others? Well, this graph is decreasing to the left of 0 and decreasing to the right of 0, right? It's decreasing over its entire domain. Therefore, its derivative should be entirely what? Negative. Yeah. So that's going to be below. So this would be helpful like on a multiple choice if you're trying to match it up. All right, now let's look at how they're negative. Way out here, I'm drawing little tangent lines. That's like, and you can actually give it like a possible slope. That's like negative 1/5, we'll say. And then right here, that's like a negative 1. And over here, that's like a negative 100, right? You can kind of just make up values of the slope. Those are reasonable, aren't they? You got your 45-degree slope and then something that's not as steep and something that's steeper. Now look at your values that you made up. What's happening with those values, Ben DeLay?
values are increasing.
No, they're not. The slopes
Oh, sorry, slopes.
are decreasing. The steepness is,
Steepness is
ah,
increasing.
steepness is getting bigger. It's getting steeper. Well, the values, -1/5, -1, -100, it's becoming more negative. Okay. So how do I draw then a derivative? I'm going to leave those values there. I'm going to do the derivative in green, just so I can leave those there. Okay, we'll sketch it in green. So over here at this x value where I drew a -1/5, I need to draw a slope that's like a -1/5. It might be right in there somewhere, actually. Over here where I drew the slope of -1, I need to draw a y value now that's -1-ish. Well, that's going to be somewhere in that vicinity. And over here where I drew a slope of -100, at that x value, I need to draw a y value that's like -100. That might be down here. Now, look what's happening. As I go out to the left, go backwards, your slopes are approaching a horizontal tangent line, aren't they? So your slopes are approaching 0. So as I go to the left, my y values need to approach 0. And as we go to the right, -100, -1,000,000, -1 billion, they're getting infinitely steep in the negative direction, approaching -infinity. Well, holy moly smokers. The shape of the derivative looks very, very similar in this portion as the shape of the original function, doesn't it? Yeah. So you look for horizontal tangents, but if you don't have those, is the function increasing or decreasing first? Am I sketching above or below the axis? And then compare two that are neighborly, or three of them, right? Is it getting more negative, less negative, more positive, less positive? That's the analysis. All right, let's do this one over here. Again, I'll do in red a practice slope. Oh, look, here's like -100 slope. Here's like our old -1 slope. And here's like our -1/5 slope. Now what's happening to the slopes? The steepness is decreasing. It's getting flatter. But what's happening to the numbers? They're getting bigger. We're climbing out of debt, right? We're approaching 0. So I have to draw a -100. Let's go to my slope color, my y value. At that x value, I need to draw a y value that's like -100. At the x value where I do the slope of -1, I need to draw a slope of like a y value of -1. And where I do the slope of -1/5, I need to do a y value of -1/5. And if you keep the slopes going to the right, again, they're approaching 0. And then if you work back towards the left, your slopes are approaching -infinity. So there it is. And now we'll label it. So if you were to try this, watch. Now we could verify. If y was actually equal to like 1/x, which is x to the -1st, if that were the blue one, then look what happens in green. This is actually -x to the -2nd, which is -1/x squared. X squared is your volcano graph, right? That opens straight up on both sides. And what would the negative do to the graph in any graph when it's out in front like that? Reflect it across the x-axis. And that's pretty consistent with what we did qualitatively. Okay. So that's a skill. It's kind of fun, right? It's kind of like, oh, yeah. Are there more than one right answer? Yes. Are there features though that need to be consistent among all the variations? For sure. For sure. Okay. And you can practice some of those in the worksheet. What time are we in? So 105? 105. Okay, good. Nice. All right. Now let's go backwards. When you're going backwards, which is the next part, you're going to have a starting point. Okay. Our values had to be on the x-axis when we had local max or mins, but then how high or low we went varied. But if you're going backwards, you need a place to start. So you're going to be given a place to start. Assuming that f of 0 equals 0. Oh, I like that point. I like that point. That point is also called the what? Origin, right? Adam and Eve, Adam and Eve. Sketch a graph of f if possible. Oh no, that's a period, right? Sketch graph of f, period. Okay, got it. And then if possible, determine the x value or values where f achieves its max or min. Ugh. Okay, I'll deal with that later. But note to self, when it says max or min, is that absolute or local? Global or local? If it doesn't specify. No. This means global, right? Or absolute. I'm sorry, I changed it. Local or loco? Right. Local or global? The global sounded like local. Right. Usually you say local and global, and then you say relative and absolute. Those are kind of how they pair up. But remember, if you don't specify, everyone's going to assume that it's the global, right? Which can occur at critical values or endpoints. All right. So first things first, we're going to go to the origin. So here is part A, B, C, D, E, F comes next. All right. I'm going to do this in red because it contrasts better, right? It's like a bright orange, which is the complementary color of blue. All right, but we're going to do like unicorns and cougars. All right. So, hey, 0, 0. Boom, got it. All right. Now, you're going to like this. When we're going backwards, we got to think differently, right? When we're going backwards, here's how we have to think right here. Remember this in the beginning? That's how you have to think. Because that's what we were doing this whole time. We were talking about characteristics of F, and that's how we were using the graph, okay? So here's a quick way to do it. It's nice that they gave us a starting point at the leftmost point, okay? If they had given us a starting point like somewhere in the middle, you could do the analysis that I'm about to show you, but then you'd have to come back, like wrap around and then do it from 0 to 4, okay? So here's what we're gonna do. Every time we get to a change in slope on this graph or a change in sign of this graph. In other words, anytime this graph changes from positive to negative or negative to positive, or the slope changes from positive to negative or negative to positive, we're going to stop and reframe. Because the idea is if we know what the sign of F prime and F double prime are, then we know on the interval which one of those it's going to be, right? It's going to be either that, that, or that. So we're going to analyze those two things. Looking at the y values first. The y values of F prime will tell us if we're going to be sketching it up or down. And then we're going to look at the slopes on that interval, and that'll tell us how we're going up or down, right? Concaving up or concaving down. Got it? All right. So if you want to make a note to yourself, because it's going to be fun, right? Every change in sign of the y value, that's going to be up or down, F, or the slope value, which is going to be CC up or CC down on F. We're going to recalibrate. And we're going to decide which of these 4 pieces we use, okay? Watch, it'll make sense when we do it. Ready? On the interval from 0 to 1, the graph of F prime has negative values. See that? So F is decreasing. But the slopes of this graph are positive. So F is concave up, right? So here's how we're going to do it. It's real quick and easy. We're going to talk about y values first and slope values second. Negative y values, positive slope. Negative, positive, negative, positive. Now we shifted up 1 unit. Negative, positive now means decreasing, concave up, right? Decreasing, concave up. So decreasing, concave up like a cup until we get to 1 where there's a horizontal tangent. So we curve in, right? Now on the next interval, let's highlight them. We'll alternate colors. The next interval is from 1 to 2, right? On this interval, we have positive y values, positive slope. See that? Positive, positive. That's what I like. Now shift it. Positive y values, positive slope now shifts up to increasing concave up. Increasing concave up. Increasing concave up. Okay. Now, when I get to 2, am I on the x-axis or am I a little bit short of it? I don't know. That's up to you. That's the variability part. Okay. Now we're on the next interval. I'll alternate yellow, pink. Okay. On that interval, we have positive y values, negative slopes. Positive y values, negative slopes. Positive, negative shifts to increasing concave down. So now I come over here, increasing concave down until there. Now again, I don't go horizontal there, right? Don't come in and go horizontal because the slope there is not 0. So come in at some kind of angle like that. All right. Now we're on the next interval, right? On the next interval, the function is increasing, positive and increasing. So positive y values, positive slopes, positive y values, positive slopes. Shift it, that means now increasing concave up, increasing concave up, increasing concave up until we get to 5. How high are we? Oh, we're major high, right? We're high on math right now. Woo! Okay, hope our teeth don't fall out. Yeah, no, that's different. All right. Now we're on the next interval, purple nurple. All right. Oh, purple, pink, sorry. Now on that interval, we still have positive y values. So the function's still increasing, but now it's negative slopes. So it's concave down, right? So increasing concave down, increasing concave down. And now when we get to 6, there's a horizontal tangent line because 6 hit 0. So we need to make sure we go horizontal there. I might kind of get an extra curve in there to make sure it goes horizontal. All right. Now from 6 to 7, help us out. Who's going to help me out? What are we doing on 6 to 7? Uh-huh. Decreasing concave down. Good. Because we have negative y values, negative slope. Negative y values, negative slope. Negative, negative, when you shift it means decreasing concave down. Decreasing concave down to about 7. Somewhere in there, right? And then finally on the last interval, on the very last interval, we're not on the last interval yet. We have to go from 7 to 8, right? Anytime the slope sign changes or the y value sign changes. All right, so on that interval, we have negative y values, positive slopes. Negative y values, positive slopes. Negative, positive shifts to decreasing concave up. Decreasing concave up like up. And then we go to 0, a horizontal tangent. And then finally, on the last interval from 8 to 9, I like to end this way, right? Positive y values, positive slopes, positive, positive shifts to what, Ethan? Thank you. Hey, yeah. Yeah, increasing at an increasing rate. We're looking for curvature. So increasing concave up, increasing concave up, increasing concave up, somewhere to there. Okay. And then boom. And now I'm going to label that as F. Now notice that graph could have been anywhere vertically, right? If they gave us a different starting value, that could be anywhere, because notice that does not change the y values of the derivative, because these graphs that I'm moving up and down, they only differ by a vertical shift, right? How do we vertically shift something? We just do what to the end of it? +1, +2, -3, -4. What's the derivative of a constant term? 0. Now, is it possible to determine the local max or min, or the absolute max or min? The absolute minimum occurs at x equals 1, no doubt. The only other possible location it could have occurred was at 8. But there's no way it's going to get lower at 8 than it did at 1. 2 reasons. It spent more time, if you will, going uphill. It went uphill from 1 to 6. That's 5 seconds. Okay. And then it only went downhill for 2 seconds. Okay. The other thing is the rate at which it was going up. Notice this value up here at x equals 5 gets up to about 3. That's like going up at like 3 miles per hour, which is at a faster rate, not only a longer time span than what we were doing here, which is like -2.5 at the very start. So there's no way. So the absolute minimum is at x equals 1. Is it possible, though, to determine the absolute maximum location? It's not going to ask you to justify yet. There's 2 candidates, right? It could be at x equals for the absolute max. It could be at x equals 6, or it could be at x equals 9, right? Absolute extrema concur at endpoint. Do I know for sure that the graph doesn't go higher at the right endpoint than it did at 6? I don't. For yours it does. For mine it might not. That one is less obvious. You're not going to be asked that. Okay. If you're asked to give a determination where the absolute maximum occurs, it's going to be obvious, right? So we can't tell, but those are the two candidates, the local max and the endpoint. All right. So the only difference, we'll finish this tomorrow. Okay. I do want to get to example 5 where we have data and then look at this calculator question. I may skip example 4. You might want to do that one for enrichment. The only difference is here you have a cusp, right? The derivative is undefined, changes from positive to negative, but the function is defined. Concave up, concave down. All right. Y'all have a great sea lunch. Thanks for being such a captive and captivating audience. Bye, Juliana.
Bye.